Oh, hello everybody. Now we are on week 12. There is only one week left, and it is the topic before the last topic. So today I'm going to cover two important parts of hydrology. The first one is stormwater runoff calculations, and the second one is how to determine the capacity of a storage reservoir. Actually, these both are important topics, and you are going to use them in the next lecture. It is water supply, an elective course if you are going to take it in the next year. So you are going to use all those principles in the calculations of storage reservoir calculations and even stormwater runoff calculations. So I want you to listen me very carefully because there are some analytical parts here to solve the problems. It will be good for you to follow me carefully and follow everything, then learn it. It might be a little bit difficult if you try to learn it yourself later. Okay, so let's have a start. And this is a kind of reminder for you from the earlier week, and it is telling us that the most critical things in hydrology, especially for the civil engineering works. Okay, so the rain, water, runoff calculations, and it is mostly related to type of the slope and terrain and other things. So this is a kind of reminder for you to update that, what kind of information you are supposed to require in this section. So what you are going to learn today, you will learn again stormwater runoff calculations and reservoir calculations. So okay, let's continue. Okay, please have a look at this figure. You will see that in the okay, the first thing is first. Do you know what is watershed? Okay, anybody knows what is watershed? Do you have an idea what it could be, a watershed? Okay, so let me explain. Watershed is a geological structure that collects water, okay, after any precipitation into one reservoir. For example, there is a watershed for every typical lakes. And just imagine that any lake in Kazakhstan or any river for Kazakhstan, and there is a watershed for that river, there is a watershed for that lake, and also there are watersheds for cities and some geographical locations. So basically, all the precipitations will be yielded, okay, into the watershed, and it will flow over a reservoir. The reservoir could be a kind of natural lake, or it could be a kind of engineered reservoir like a dam. Okay, so I think it is clear that what is watershed. Okay, do you have any questions? Did you get it what it is? Okay, thinking that way, while you are, for example, thinking that way, if it rains, some part of that rain over the region will go to will go to Lake A, and other part of the rain and precipitation will go to Lake B. It means that in that region you have two watersheds. The watershed 1 is for Lake A, the watershed 2 is for Lake B. Okay, so this is typically what we have. So what you are going to learn today, how we can estimate the amount of water, okay, we can collect in a watershed. This is very important in civil engineering because this calculation is the main principle to make a design for dams and reservoirs. Okay, so if you like to make a kind of dam to hold some water for irrigation, aggregation, or for some irrigational purposes, or for water supply for the cities or towns, first thing is first, you should learn, or you should analyze that how much water you can hold in that watershed. So while we are making this calculation, the main principles and the main mechanisms of the water movement or the water cycle is critical. And look at the figure on the right. Okay, you are going to see that it precipitates on the ground. After precipitation, a certain amount of that rain is able to infiltrate into the aquifer. Then it is going to flow into the reservoir. Okay, so it is not as 100% efficient. The efficiency of infiltration and transportation of the precipitated rain may differ from region to region, from watershed to watershed. Sometimes it is 50% efficient, sometimes it is 60% efficient. It go up and down. And also you are going to lose some water in the watershed by evaporation. I remember that in the earlier week, one student was asking me that, where is the evaporation? So it is time to talk about evaporation. Okay, so if you are talking about a watershed after rain, okay, think in that way, it rained, okay, it precipitated a million tons of water on the watershed. And the research question, now engineering question is here that a million tons of precipitation you had in the watershed, but how much of that water will be collected in the reservoir? Okay, did you get the trick? In order to know it, you know the infiltration ratio, you should know the evapotranspiration ratio and some other stuff, and now you are going to learn it how to calculate. Any questions, please? Okay, let's continue. So simply, the calculation principles of water balance in a watershed, okay, is given with this equation. It is quite simple. The net amount of water, okay, in a watershed at a given point can be calculated with this equation, and here Q is the stream flow, okay, I mean like a river flow or stream flow. This is actually what we can get as an actual flow. This is the actual we are going to calculate, and in order to estimate that flow, we need other parameters, the amount of precipitation. And okay, I want your attention to the points and minuses. Okay, point, I mean, if it is plus, it means that it feeds water. If it is minus, it consumes water. For example, here precipitation is plus, okay, because it feeds water into the watershed. But what about evapotranspiration? It is minus, right? Because you are losing some water because of the vaporizing and respiration of the plants. It is minus. So let's keep looking at this equation. It is typical mass balance equation. Actually, it is very simple. So the amount of precipitation will be added. Is there any import of water into the watershed? For example, if you have a river system, and if that river brings some water into the watershed, it is going to be considered as an import, and you will add it. Any evapotranspiration, it means that evaporation and transpiration from the plants, okay, these are considered as a losses. They are minus. You will subtract it. And also, is there any net export of the groundwater? It means that some of this the precipitation will stay in the ground. Okay, it will be exported. Okay, it will be exported into the ground, and it's going to stay there. It is not going to flow into the reservoir. You may also consider this as a wetness of the ground. Okay, so the wetness of ground will keep a certain amount of water, and it is minus. And also changing the moisture of the storage is considered as a kind of minus. Sorry, guys, there is a noise. I'm going to close my door. Sorry, guys, there was an IT guy here, and I have to tell him that I am teaching. Sorry. Sorry for the interruption. So this is the basic equation. And I think it will be easy for you if I show you one example and let's solve a problem together, and then I think you are going to understand in a better way. Okay, by the way, do you know what is this, guys? What do you see on the screen? What is this? Okay, these are called water pans. Do you remember that in earlier week I told you that in meteorology stations the amount of rain is collected in one point, okay, and they are measuring the amount of rain by using some measurement equipments. Actually, this is a kind of equipment which is used to measure the amount of rain and also amount of evaporation. So this is a pan, a large surface. They are filling it with water, okay? So typically they are filling it with water, and when the water level drops, for example, less than 7 centimeters in this question, then they are filling it up to 8 centimeter. So based on, I mean, also you are recording the level in every single day. It is going to show us that what is the level of or amount of evapotranspiration. Okay, so it means that how much water on a surface you are losing in that particular area in every single day. So this is a kind of equipment. That's why I put it here. And let's read this question together. And there is also data on the right side, and we will solve the problem in the next stage. Okay, let's read what it says. A water budget is needed for a proposed site in Almaty. So what you are going to do, you are going to construct a dam in Almaty, but in order to make such a kind of reservoir, okay, first thing is first, you are going to analyze the precipitation data and evapotranspiration data to go further steps. So in this case, a class A pan, this is a class A pan, this is the name of the equipment, is maintained near the reservoir to determine daily evaporation. So we have a reservoir there, like a lake, okay? So this is located next to lake, and this device is going to be used to estimate the evaporation amounts. And it can be assumed that the coefficient to convert pan evaporation to ET lake is 0.7. And also you remember that we were talking about area reduction factor in the earlier week. So if we are talking about a lake surface, which is a large surface, it's an area surface, in this case also you should use a kind of coefficient. So for example, if you find the data by using this equipment, and if you multiply it with 0.7, you can find the evaporation on the lake. Okay, this is the correction factor to find the value in the lake by using a point measurement system. And also daily precipitation and water levels are given on the right side, and this equipment is used to make those measurements. And here it says that the maximum height of the pan is 8 centimeters. It means that, look at that, the water level is 8 centimeter maximum, but if it drops to 7 centimeters, then engineers are adding water and filling it up to 8. Okay, so let's look at data. It starts with 8. It goes down. Why? Because every single day water is evaporating. Okay, you are losing some water. Look at here. And this is the rainfall. Also, you are having some rainfall and you are losing some water. Even though you are having some rainfall, the level is dropping down. And when you reach to 7, engineers fill it with 8 at this time. And in the next day, it dropped again for 7.95. Did you see that? So you should first check this data when it is filled up. Okay, so at this point, I just highlighted it for you, but in the questions in your exam, it is not going to be highlighted. You should find it. So it is going to go up again for the 8. So that's why the data is jumping up here at 8. And now the question is that I want you to calculate the daily evaporation lakes in the lake. Okay, so this is the problem, and let's go and try to look how to solve this problem. You are supposed to follow some steps to make the calculations. Actually, these are basic arithmetics, guys, for mass balance. So what we are doing here, basically, we are doing a kind of mass balance calculations, and this data is given as rainfall amount, and this data is given for water level in the pan. And noted that rainfalls are plus values. It means that you are adding water level on the pan, and this is the evapotranspiration. Actually, this is evaporation ratio rates. You are losing water here. Okay, so that's why this value will be added while this value will be subtracted. And in order to calculate the EP, evapotranspiration rate in the pan, okay, in the pan, what you will do, okay, in the first one there is nothing because we are starting in the first day with 8, there is no change. In the second day, I put here how to calculate for you to show and demonstrate that the calculation principles. So what I did, let's follow. Okay, I took 0.25, this is plus, okay, this is rain, adding the level, and I added also 8 because 8 is the previous level, and then I subtracted the ending level 7.95. okay, so forget about the rain and let's look at here what you will see. If you subtract 8 and 7.92, you are going to see that this amount of rain, okay, you are going to lose. The amount of water you are going to lose, and if you add that amount of rain, the total amount here is 0.31. okay, so you will calculate first EP pan values, and it's 0.31, and then you will keep doing the same arithmetics, okay, but don't forget that when you reach the refill section, you are going to use not 8.0.7 here, you are going to use 8 because the initial value is 8 because it is refilled up. Then it will be 0.10. So you are going to calculate everything on the EP, and for EP lake, it is simple. You are going to multiply this value with, what was the value? 0.7, okay? If you multiply the pan values, evaporation values with 0.7, then you are going to find the evaporation values for the lake. So simply, this is the ending table, and this is the solution of the problem. And you may see that okay, sorry. Okay, you may see here that the evaporation amounts calculated, and these are the evaporation amounts for the lake calculated. Okay, now you learned how to calculate the evaporation rates by using the data and by using the equipment like a kind of pan in the field. So logic is simple, guys. Again, I am repeating that this is basic mass balance calculations. You are going to add up inputs and you are going to remove the outputs, then you are going to end up with the value you are looking for. That's also as simple as this one. Okay, any questions, please? No? Okay, I have to proceed. And I'm going to continue with the next topic. The next topic is that how you can calculate the capacity of a storage reservoir. Okay, so in order to calculate the capacity of a storage reservoir, okay, think in that way. As I told you in the beginning, you will be an engineer, and you, for example, you will be given a task to make a kind of design for a reservoir for a city or for a town or a village, and then you are going to analyze all possible data, including rain data, okay, including evaporation data, as we did in the earlier part. And after having all those information on your hand, the next thing is that to make a calculation for the reservoir requirements. Okay, so you cannot just build a reservoir without making any calculation. This is engineering. Okay, we need to know that what is the required amount of reservoir for the town or for the city as required. Okay, a simple question. And if you are designing a reservoir, do you prefer to refer the rainwater, I mean precipitation data, which is abundant or which is scarce? I mean, think in that way. There are data for 5 years, and in 1 year, the precipitation amount is minimum. Okay, so in that year, there is a droughtness, and you experience a kind of drought period, and the amount of precipitation was minimal. But in 2 years later, in third year, you had plenty amount of rain, and it was very wealthy year in terms of rain, and you had the highest amount of rain drop in that year. So think in that way as an engineer, which year of data you like to use to make a kind of reservoir design, the drought period or wealthy period? Do you have an idea, guys?
Probably wet.
Oh, I couldn't hear you, Aslan. Repeat again, please.
Probably wet period.
Okay, why? What is your aim? What is your purpose? I mean, reasoning. How are you reasoning that you should use VLT? I mean, why? But
Because
don't
probably there
forget
would
that you are
be.
constructing a reservoir, and why you are constructing a reservoir? Reservoir is needed to keep the water when it is needed. Okay, go on. Answer now.
Oh, sorry. In this sense, probably for wet period. Oh, sorry, for dry period.
Dry period. Yes, drought period. I mean, think in that way, guys. You are going to buy a tank, okay, water tank for your home, okay. So in order to make a capacity calculation, I mean, how big tank you need, 1 tons, 2 tons, 3 tons, 5 tons, what do? First, you make a kind of calculation about your consumption, daily consumption, okay. Then what you will refer, the water costs. For example, if on Fridays, if the city is cutting water, okay, for 5 hours, then you can simply make an estimation that that reservoir is going to compensate 5 hours of consumption on Fridays, okay. So basically logic is this: we are designing the reservoirs to compensate for dry periods, okay. That's why you need data for critical low flow years. That's why it is written in the first sentence here. Look at in the first item, critical low flow means that the minimum amount of for year flow or dry year you are going to refer to make a kind of design. If water is too much, you will not hold it, okay. You will not keep it in the reservoir. It keep flowing in the river, okay. You will release it. But if it is dry, we need the water. That's why we are constructing a reservoir to compensate the needs or consumption requirements during the dry periods. And also you need data for evaporation and percolation and other things, percolation and other things, monthly basis for the losses. And also you need to have a data for inputs like precipitation data. And also you need some other information that how much water is required in the region. For example, if people are villagers and if they are supposed to make some agricultural activities, so maybe their fields or their activities requires more water than usual. So these are also parameters you should consider. And also total demand for during the each month of the year. I mean, the domestic and industrial consumption should be considered too. And these are the data you should consider while you are making a kind of, okay, design. I think it will be easy for you if I solve one problem. So this is a kind of illustrative example. And after solving, I mean, making this example, my lecture will be over. But I want your attention again. Listen me carefully what I'm doing and what I'm explaining. It might be difficult to learn it later on this course if you do not follow me right now, okay? And ask me if you have any question. And let's read the problem together first, then we are going to solve it together. Okay, you see the table on the right. It is the data which will be provided for you, for example, in the exam. And the table on the right gives the monthly inflows, okay? Inflows means that the amount of water inflowing, okay, into the reservoir, into the watershed. It is like a river flow. So you will see that there is no flow in January and February and December. The river is, or the inflow is not occurring. There is no water input. During the critical low water period at the site of proposed dam, and these are measured in the critical low period. So it is good, we can use it. And the second data is about the corresponding monthly evaporation and precipitation at the nearby station. But please note it that this is evaporation data for pan measurement. It doesn't mean an area. So you have to correct it with by multiplying it with an area factor. And the estimated monthly demand of the water are also obtained. Okay, so we have also the water demand in the area. You see that in the area, I mean, the people or the region demands less water in January and February, but the water demand is going high in spring, maybe some agricultural activities. People need some water to plant their crops. And also they need more water in the October, December, and November. So this is the demand data you will get, you already get from the area. And prior water rights require a release of full natural water flow or 6.5 hectare per meter per month, whichever is less. I'm going to explain what it is. Okay. Then assume that 35% of the rain fall on the area to be flooded by the reservoir as reached to the stream in the past. It means that the efficiency of the rain is 65%. Okay. So you are going to lose 35% of the precipitation. And this is the focus area, water storage area. I mean, so the water storage area or watershed area is given as 520 hectares. It is the watershed area we are going to use to calculation. And then the panel operation rate is given as 0.7. So when we want to convert this amount into the area, then you are going to use 0.7. So this is the data. And also I am going to explain you that what is 6.5, okay, 6.5 water right. Water right means that this area has right to reach 6.5 hectare per meter water in every single month. And you will see that in these 2 months, they are not reaching the rights, okay? So they are deficient in terms of water, and there are no other months they are deficient. So it means that you are going to construct a reservoir and you are going to feed those people or those region on January and February to satisfy their demands, okay? That's why we need a reservoir, and this region is suffering from the problem, okay? This sorry, this is not correct conclusion. Just forget about it, what I said. It is something else. So the natural rise size 0.6, it means that, okay, when the water is flowing like river, you cannot collect water, okay? You cannot collect water if the amount of water is less than 6.5. It means that on January, February, March, and April, okay, you cannot hold water. It is against the human rights. This river should keep flowing as it is during these 4 months because the region need that water. I mean, plants need that water, animals need that water. I mean, the nature itself needs that water. And also you cannot keep water in November and December. It seems that if you construct a dam, you will be able to hold water only from May to October. In other months you cannot hold water. You should release all the flowing water into the nature because that amount is required by the nature itself, okay? This is a natural flow required by the plants, by the animals, and by the terrain, what you have over this area. Let's solve the problem. Okay, so in this part, you see that I highlighted in red the period you can hold water. In the other months, you cannot hold water, and the water should keep flowing. And these are in flow. So that's why downstream flow on the river is going to be the same in these months. Okay, you are not going to hold any water. There is no flow here. Okay, there is no flow here. But in March, the amount of the flow is 2.7. Then we are going to release the same amount of water. We are not going to keep anything in the reservoir because it is less than 6.5, and the same here. But at this point, okay, at this point, you are going to release 6.5, then rest will be held. It means that you are going to hold 0.7 hectare per meter water in the reservoir. And that's why I put here 6.5, 6.5, 6.5, 6.5, 6.5, and rest. These are the downstream requirements for the water. Is it clear that how we are calculating downstream requirements? Okay, no comments. Then let's continue. Then you will calculate the evaporation rates by using the data. It is straightforward, guys. The equation is given here. You are going to multiply this value with the 0.7, the coefficient for the area. Then you are going to multiply the amount in the pan with the reservation area and divide it 1,000. It is quite straightforward. And by using this data, you can calculate the evaporation ratio. And if you are asking me that why we are dividing it 1,000, because the value here is millimeters, and we are going to convert it into meter. Okay, that's why we are multiplying it with 1,000, dividing it in 1,000. Then these are the amounts of evaporation per meter area, per meter rain over area, total area. And don't forget that these values are calculated, are multiplied with the total area. So here we have 9.1 meter water. Okay, so you may think in that way, you have 9.1 meter height of water received in that period. Okay, let's continue. And in the third step, you are going to calculate the amount of precipitation. It's also easy. You are going to use precipitation data to calculate the total amount of precipitation, and you are going to use this equation. And don't forget that in order to calculate the area precipitation, you should use the area reduction factor, which is given as 0.65. It means that 65% of the water reaches to the reservoir. It means that you are losing 35% and efficiency is 0.65. And use this equation, and then you will calculate the precipitation data on the right. And guys, this is the last stage. And let's look what we are doing here. And this is mass balance equation. Actually, it is quite an easy. And let's look at the data, what we have. And let's try to identify what we have as an input and we have output. So inputs means that you are going to add up. Outputs means that you are going to reduce. Okay, so inflow is an input. These are just data. We converted them into other parameters. We are not going to use them. And it is in the units of hectare meter. That's okay. And demand is also hectare meter. This is good. So demand means consumption. It is minus. Downstream requirements. This is the requirements from the vegetation and the animals and the area. It is a kind of minus value. It's a consumption. Evaporation is also a consumption. You are losing some water by evaporation, and it's also minus value. Then precipitation is input value. This is plus. So this parameter will be added. These three parameters will be subtracted, and this parameter will be added. Then if you make this math, you are going to find those values. And here I put NA. NA means you are going to end up with positive numbers here. And if you are making a kind of storage calculations, you are not going to add the positive numbers, okay? You will remove them. You will remove them, the positive numbers. Then the total of this amount will give you the amount of reservoir required, okay? So in this region, in order to sustain the region as it is designed, you need a reservoir which is capacity to hold 217 hectare meter water. Okay. So if you are going to have a kind of, for example, 20 hectare area, water holding area. Okay. And if you are going to have a kind of 20 hectare area as a kind of dam, for example, then you can easily calculate that what should be the depth of the or height of the reservoir by using this value. So this is a typical requirement, or this is a typical capacity unit, and you are going to use this capacity to calculate the reservoir height and other stuff. Okay, so this is an essential calculations in water engineering for reservoir or dam calculations. Okay, this is the end of my presentation for today, my lecture for today. Now it is your turn. If you have any questions, please ask. Diaz, do you have any question?
No.
Is everything okay?
I think
Okay.
yes.
Thank you very much. Thank you very much, guys. And it seems that everything is okay. So I am ending my lecture now.
Yes.
And
In the final exam, will we have like 50-50 for hydraulics and hydrology?
no, it is not
Or-
going to happen in that way, Tomiris. What I am thinking that maybe I can make it 40-60. 60 is from hydraulics again, and 40 is from hydrology. Okay.
Okay.
So if I ask you, for example, 5 questions, you may expect that you are going to get 3 questions from hydraulics plus 2 questions from hydrology. Okay.
Yes. Okay.
Okay.
And what about the assignment?
You are going to get one more assignment. It is left. So I am going to give the assignments this week, most probably. Okay. And then you are going to have one more week until next week, the last week, then you will complete it. So I gave you 3 assignments and the last one is waiting for you. And most probably I'm going to assign it in this week. Okay. Until the end of the week, I will assign it and I will give you 1 week more to solve it. Is it okay?
Yes.
Okay.
Thank you.
I think we have done all the clarifications. Okay. See you next time on Thursday, guys. Bye-bye.
Thank you. Goodbye.
Thank you.
Goodbye.
Goodbye.
Thank you. Goodbye.
Thank you. Bye-bye.